It's a great pleasure to introduce Vahid Sandoghdar, who is a director of the Max Planck Institute for the Science of Light in Germany, and also the founder of the Optical Imaging Center Erlangen and Max Planck Zentrum for Physics and Medicine. So Vahid is very well known and a pioneer in the field of nano-optics, where he merges various research areas to investigate the interaction between light and matter at the nanometer scale. He has a broad research interest, and including the interferometric scattering microscopy that we have heard about, and with a special emphasis on controlled biophysical studies. So his talk will be titled Label-Free Direct Detection, Sizing Imaging of Single Proteins and Bioparticles. Right.
Yeah, good afternoon, everyone. And of course, thank you very much, Frank and Felix, for including me here and for the punishment of giving the last talk. I understand it's an honor, but I particularly thank all the attendees to stay here instead of going to the sun in the beautiful Barcelona. So I will talk about, in essence, our interferometric scattering microscopy work, but instead of going through lots of details of experimental endeavors and little tricks and all of that, I will try to kind of put this in the context. So maybe half of it would be results and the other half would be more a little bit of a tutorial. So let me start by confronting you with the simplest microscope that you've ever come across, or imaging mechanism, and that would be just looking at the shadow of something in bright field microscopy. And what I would like to emphasize is that the image that is formed here is a shadow, but actually it's the result of an interference effect. And if you were to write the signal there, you could write it as the sum of the electric field of a reference. Sorry, here, it should be incident. The incident field, but you can think of it as reference for the rest of the talk, plus the electric field of the object. Now, in the macroscopic way, this is how microscopy evolved all the way through from the 16th century to the 20th century. But you can, in principle, do the same thing at the single molecule level and just see a shadow of a single molecule. And that would be doing bright field microscopy on a single molecule. Now, you usually don't think that you should do that. And the reason for it is that if you think that you're going to illuminate an object, then the amount of light that will be taken out is given by some kind of a cross-section, and that cross-section for a single molecule you think must be very small because the molecule is small. Now, again, this is a simple extinction type of arrangement. You have an object, it extinguishes some of the light, and therefore the light that you detect along the same k-vector is going to be smaller by the amount of the light that was lost along the way. But also this phenomenon is, in principle, an interference effect. And in particular, you can think of this as plane waves interfering with the light that is scattered by a nano-object, a single molecule. And that's usually a dipolar wave. So if you add these two up, you end up having destructive interference in the forward direction. And that's the same thing as what you would describe here. That is, that's how you would calculate a scattering cross-section. So this kind of formula is going to be basically everywhere in everything that I'm going to show you now all the way to the end. So it is really important to realize that your most basic light-matter interaction is a scattering process. All right, now we actually did the experiment that I demonstrated on the first slide. This is literally a shadow of a single molecule at room temperature. So the arrangement is as simple as you would think. You focus light onto a sample that has sparsely located single molecules, and as you scan this across, every time that the molecule is in your focus, you get less light in transmission than before. But the amount of that light that is missing is of the order of 10 to minus 6, and that's because the cross-section of a molecule is given by the simple formula. Lambda is the transition wavelength for the ground state to the excited state of that molecule. And gamma 0 divided by gamma is telling you how dephased the whole system is. Gamma 0 would be the rate of spontaneous emission, and gamma is the homogeneous line width. And that ratio is typically of the order of 10 to minus 5, 10 to minus 6. And you see here also that we're measuring something of the order of 10 to minus 5, 10 to minus 6. So this is now, again, a very straightforward thing. You might think of this as an absorption experiment, as an extinction experiment, and you don't necessarily think in terms of interference. But again, this is an interference phenomenon. 1. 2 is that you can see a single molecule in a simple transmission measurement. Now, the signal that is actually reporting about the molecule is not so much the signal that was missing, it's actually the signal that gets to your detector. And that signal is the electric field that is scattered. Now, the field that is scattered actually also has a phase shift if there is absorption in the system. So whether your system absorbs or scatters, at the end, the final kind of principal signal that you get is the scattered light. All right, now we've done that experiment also with a molecule that is frozen at 1.5 Kelvin. And when you do that, the absorption cross-section goes very close to lambda squared divided by 2. So that ratio, gamma 0 divided by gamma, that was 10 to minus 6, becomes more of the order of 10 to minus 1. And that's why what we are seeing now is a more than 10% drop in the laser intensity as it encounters a single molecule. So, and this is more from our quantum optics type of studies. There are all kinds of things that we've done, taking advantage of the fact that a single molecule is intrinsically, just like a single atom or a single quantum dot, is intrinsically a very strong scatterer of light, so you can get a very strong extinction from it. Now, when you go to a nanoparticle, you don't have resonances necessarily, and what matters is the polarizability. So you know that the electric field that's scattered by nanoparticle is the polarizability times the incident electric field, or is proportional to that. And the polarizability is given by the simple formula. There are two things that are important there. One is that the ratio of the dielectric function of the particle and its medium matters. That's important. That's all in this Clausius-Mossotti fraction here. But what's much more important is that your polarizability scales with volume. Your polarizability has a dimension of volume. So that's the thing that intuitively tells you that a small particle scatters little and a large particle scatters a lot, but proportional to the volume. Now, polarizability is a more fundamental quantity, and knowing your polarizability, which of course is a complex quantity because your dielectric function is a complex quantity, knowing your polarizability, you can figure out your scattering cross-section and your absorption cross-section. This is all textbook stuff. You've all seen it somewhere. All right, so this is a little bit of the basics of kind of simple light-matter interaction in the Rayleigh scattering regime for a single molecule that has a resonance, for a nanoparticle that doesn't have a resonance. What we've been doing in the past 20 years now started partly from this work, where we were actually at the tail of single molecule microscopy from the 90s. We're looking for ways to do single molecule or single nanoparticle detection without fluorescence. And that was because everyone already knew that fluorescence is limited. It has lots of issues. You don't always want to look at things that are fluorescent. Most things in life are not fluorescent. So we were looking for other ways of doing this, and we realized that we can use scattered light to detect very small particles. In this paper, we demonstrated detection of very small gold nanoparticles using scattering. These are examples of 20 nanometer and 10 nanometer particles. And we showed that the reason and the signal that we're getting is an interference phenomenon. So that's kind of how this whole ISCAT work started. But we soon realized that there was nothing special about gold nanoparticles. Of course, we were also interested in these gold nanoparticles because that was early 2000s was the beginning of what you call now plasmonics. At the time, the word almost didn't exist. So we were interested in that. But we realized that there's actually nothing really special about gold nanoparticles. You would think that a gold nanoparticle scatters a lot, but remember that volume is a lot more important than anything that has to do with the index of refraction that you can do. You change the size of your particle by a factor of 2, you get a factor of 8. So the volume is much more your friend than index of refraction. And we realized that a single virus is actually also a nanoparticle. In fact, it could be quite large. You've seen now several talks about viruses, and you know from daily magazines that a coronavirus is 100 nanometers large. Now, you can have a virus that is as small as 20 nanometers or as large as a few hundred nanometers. This virus that we looked at way back when we were still in Zurich had a diameter of the order of 50 nanometers. And in those early experiments, the way we were doing the experiment was as depicted here. Our nanoparticle is sitting on a substrate, and we're illuminating it from below through the microscope objective. And we're detecting the scattered light in reflection. And of course, we're also picking up light from the interface, and it's these two fields that are now interfering. So in the normal extinction, it was the incident field that interfered with the scattered field in the forward direction, and now it's the reflection of the incident field that is interfering with the scattered light in the backward direction. Anyhow, these were some of the movies and images that we could record from an individual virus, in this case jiggling around on a synthetic lipid bilayer. So now, after many years, we have understood a lot more what is happening, and in a way, I think it's important to unify what we and many other labs have done so that the actual physics becomes clear. So what we are now thinking is that ISCAT is every time that you detect a nanoparticle through scattering and interference, because that's what the name says. And in that light, you can do it in lots of different ways. The same way that you can do fluorescence in different illumination and detection ways, you can also do ISCAT in different illumination and detection ways. These are just a few examples. I showed you the extinction version. That would be a transmission ISCAT, and you can do that confocally or in the wide field. And the very first version that we did was confocal in that paper from 2004, but it was in reflection because we looked at the light that was coming back from the interface. And you can, in principle, of course, also do ISCAT using an external interference, and that's what you would normally call holography. But holography is typically done on larger objects, or historically. But if you do holography on a nanoparticle, that is nothing but ISCAT. And again, you can also do reflection wide field, and that happens to be the most common mode because it's one of the simplest ways of getting fast, meaningful data from a large area. Now, I told you about bright field microscopy, but there have been lots and lots of different techniques that have been developed over the past 50, 60 years, and they all explicitly or implicitly use interference, and they're all related. They're basically all the same physics. So phase contrast, differential interference contrast, what you would call interference reflection microscopy, quantitative phase imaging, digital holography, all of that is using this equation. And in that light, they're all the same. Dark field microscopy only uses the intensity of the scattered light, and therefore is proportional to v squared, or d to the sixth. And when you use only, when you go to very small nanoparticles, and detect the whole thing, this signal drops very rapidly so that what becomes important is this cross term, and that's typically what you call the ISCAT signal or the interference signal. Again, the actual physics is not new. I think what we have contributed is to realize and to be hard-headed about detecting very, very small particles in this very simple mechanism. Sometimes in the early days, we were getting referee reports that said, "You're not doing anything special." And our answer was, exactly. But the point is that without doing anything special, you're actually detecting very, very small things. So detecting a very small signal in this type of way from particles. Now, the smallest things that we've detected are single proteins, and our single protein work was the tail of our single virus work because we wanted to, of course, push the limits. That we did when we went to Erlangen. Marek Piliarek was an excellent postdoc who worked on this project almost single-handedly. So imagine that you have your sensor surface. You might have functionalized it or not. Now, if you look at the surface in an iSCAD microscope, you would get a speckly type of image. And this is one of the things that, of course, many people knew about, and that's why they didn't do it a long time ago. If you use coherent illumination, you get speckles. Now, the kind of speckle that you get, you get speckle because your substrate is not 100% atomically flat. There could be slight modulations of topography, even if it's just 1 nanometer every few hundred nanometers. And there could be tiny, tiny changes of index of refraction in homogeneities, and they all would give you a speckle. But we live with that, and we realized a long time ago, actually, that if you just subtract these two, you can flatten your field. And the critical thing was to realize that a speckle is not noise. A speckle is a fixed signal, and it's your background, but it's constant, so you can subtract it. And by doing that simple trick, we could show that we could detect individual proteins as they landed. Of course, what you're doing here, you're taking advantage of a temporal kind of encoding of signal. If the protein is on the substrate and you give it to me, I will never know what's there. But if the protein lands in front of my eyes, I will be able to tell when it lands. So these are footprints of individual proteins as they parachute down onto the substrate. Now, we looked in that work at different types of proteins. So you can have large proteins, you can have small proteins. And every time you run a whole bunch of videos, and you can analyze the darkness or the signal size from each one of these spots and make histograms. So there might be some background there, but then you go beyond that, and that is now giving you a certain contrast. But we also realized that this contrast actually scales linearly with the mass of the protein. And it might be a little surprising, but that's just how it is, that it turns out that the density of protein matter seems to be more or less constant. So our signal is proportional to the volume, but it turns out to also be proportional to the mass, which is a very nice kind of gift from above. So, and this set the ground for doing actually what is now called mass photometry. And the term mass photometry was coined by Philip Kukura, who now has his own group. He's had his own group for more than 10 years now at Oxford. And they worked together with a whole bunch of biochemists and mass spectrometers, and they really went after this and demonstrated that they could do this in a very quantitative way. And in particular, they could show, for example, that you can tell a difference between monomers and dimers and trimers. And this seems to be quite important for anyone who does mass spectrometry or does protein work, because in any sample that you have, you never have pure monomers. So it's important to actually know what you have. And so they have actually spun off a very successful company called Refine, and many of you might have their devices at your institute. More recently, we tried to push the limits even further because what everyone was doing up to then was more proteins of the order of 40 kilodalton, because that's where we were running into the background noise. And I'm not discussing all those details, but you're welcome to ask me about that. We used machine learning algorithms called anomaly detection. What this algorithm basically does is tries to learn about the temporal and spatial profile of the footprint of the proteins and distinguish that from the speckle. Or what it actually does is learns what a speckle is and tells what is not speckle. And by doing that, we could push our sensitivity limit down to just below 10 kilodalton. And there, of course, there's no reason why this is the real limit. This is just where we stopped and thought that it was worth publishing now. So this is a ladder that goes all the way down to 9-point-something kilodalton. And by doing that now, we have access to analysis of proteins that are really small. They're proteins that are smaller than 20 kilodalton are particularly interesting in biomedical research. And here's an example of a protein that is 11 kilodalton, but it comes in multimers, and we're detecting those. I encourage anyone who's interested in or is working on some of these things to maybe consult this paper and try to do your own work along the line of the kind of analysis that we have here, not because it's our work, but it's more to really just set the ground for always going after your signal-to-noise ratio and try to understand why you're better than what you were 10 months ago, or better than another person who's published something similar. Because without a proper quantitative signal-to-noise ratio analysis in your paper, it would be very difficult to know whether you're doing something amazing or not. Because the kilodalton is very nice, but it would be much nicer to know where we go. There are issues of camera technology, there are issues of stability, there are issues of electronics, there are all kinds of things, and it would be very important that you identify your limit in your experiment. So we're trying to do this in this paper for our case. All right. Now, that was just in the case as if you were just pipetting proteins and you want to know what you have in there. Of course, it's a lot more interesting to go to real live cells and see what's happening there. So secretion is one application that we wanted to tackle. You know that your cells are constantly communicating with their environment via chemical exchange of material. And so there is secretion that's happening. We worked together with some of the people at the university hospital, and we had this cell, and this cell was supposed to secrete IgG. So what we're doing now in this case is we're parking our field of view to the side of the cell and just watch as these proteins are ejected. They fly and land on the substrate, and we watch them. And this is what the movie is telling you. So you literally see how these proteins land and when they land. And of course, the nice thing is that instead of preparing your supernatant every 5 minutes and to see what kind of dynamics you have, you can actually watch this in real life. And your cell doesn't see any light, so there's absolutely no phototoxicity or anything. And you can do this as long as you want. When you do that, then you can make histograms, and I showed you before that the contrast is proportional to the mass, and you can try to see what is coming out. In this case, we could verify IgG, but there's other stuff that is coming out as well, and we stopped there, so in principle, one should do more quantitative analysis on things like this. But cells actually do simpler things. They secrete proteins, but they also secrete nanoparticles. And in particular, they secrete things like extracellular vesicles. These are right now quite popular because they are kind of dealt very highly as disease markers. So these are basically like liposomes or small SUVs, but they could have proteins or DNA or RNA inside, or they could have proteins in the shell. But there are other things like viruses or lipoproteins or all kinds of other things that you could you would want to detect. So we did this work, which was published last year, and to some extent this has been already alluded to, for example, in the beautiful work of Romain Quidon, but also Achilles this morning was referring to things that go in this direction. So the technique that has been around, and you can buy a commercial instrument, is called nanoparticle tracking analysis, or NTA. You use dark field microscopy to look at the trajectories of individual nanoparticles. And by establishing the trajectory, you can use this simple Einstein-Stokes formula to you calculate your diffusion coefficient, and from that, the size of the particle if you know your viscosity and temperature. But remember that in dark field microscopy, your signal goes as v squared, which means that between a 10 nanometer particle and a 100 nanometer particle in your sample, there's a factor of million in signal. And no detector has that type of dynamic range. So NTA usually blind to smaller signals because it sees all these larger ones. And we thought that we do INTA, which is the interferometric version of NTA, which is basically just doing the ISCAT detection instead of doing dark field detection. And otherwise, we do what they did. This is a little bit of a comparison. So as a benchmark, take 30 nanometer gold particles. This is what dynamic light scattering gives you. This is what NTA gives you. This is what INTA gives you. And these are two different types of electron microscopies. So this is very promising, and of course we tested this in mixtures. That's particularly interesting because if you know you have a homogeneous sample, it's not that big of a deal to know the mean size. Here we have 3 different particles, quite on the small side, 15, 20, and 30 nanometer particles, and we can resolve them very nicely. But now what we're doing is we're doing a 2D plot, and we have more information just the diffusion constant because we can make quantitative measurement of the intensity signal. And remember that the signal is proportional to the volume, so if we take the third root of the signal, it becomes a measure for the size of the particle. And that's what is plotted here always on the y-axis. So these are both, if you want, size, but measured completely independently. And this 2D plot has more room for you to decipher different types of things in one dispersion. And these are different examples of how we have mixed different particles. And in particular here, you have 10 nanometer gold, 20 nanometer gold, and NTA couldn't detect either one of them properly. But now we have a mixture, and in addition to that, we have the same particles pegylated. And you can see that all of this comes out quite nicely. So this might be helpful. The last thing that we've done is to actually go into the cell. I told you that you usually have a speckle problem. And up to that point, we had seen a lot of speckle from cells. That is, you put a cell on your ISCAT microscope, and you recognize almost anything. You don't recognize anything because there's a lot of speckle. And what we noticed is that if we actually do confocal ISCAT, which was the very first thing we had done in 2004, now on a cell, we actually get beautiful signals, and we can do live cell imaging. And so that paper was published earlier this year. I'm not going to go through the details of that, just flash a few things as a kind of an appetizer so you can go and read the paper. So here is an ISCAT label-free image of a live cell. And what you see is a whole bunch of stuff. This dark network are the endoplasmic reticula. These are not impossible to see with other label-free methods, but they usually are quite hard, and typically one sees them with fluorescence. But what you also notice, you might notice in this image, but I'll show you another one, are microtubules. And those no one has seen inside the cell in a label-free fashion, as far as we know. So this is what I call a nanoscopic version of a Van Leeuwenhoek. because it's really just using the same mechanism. I'm trying to insist that this is really just basic extinction microscopy using scattered light in a live cell, but we have learned how to detect these tiny signals. We, of course, have done this in conjunction with fluorescence. We do simultaneous fluorescence and iSCAT so that we know what we're looking at. In this case, you see an image where you have the microtubule and endoplasmic reticulum at the same time, and each one of them is labeled, and therefore we can clearly identify what is what. You can then go ahead and train your neural network on the fluorescence images and then not have to do fluorescence all the time. And this is also something that we demonstrate in the paper. So you can do your, if you want, in silico specificity instead of chemical specificity of fluorescence to a certain degree. What is also particularly nice when you're doing confocal and iSCAT is that you can not just look at two-dimensional projections, but you can get three-dimensional kind of landscape of these structures. This is a three-dimensional kind of structure, part of an endoplasmic reticulum, and you see that we're resolving only a few tens of nanometers in height. And that has to partly to do with the fact that because you have an interferometric signal, if a structure goes up a little bit, then the phase is imprinted in the contrast, and when you analyze all of that, you can figure out the three-dimensional topography. So the axial resolution in iSCAT is typically much better than it would be in fluorescence. Another example of the three-dimensional kind of capability is shown here. The endoplasmic reticulum sheets were anticipated to have a kind of a drum-like behavior, so a kind of an oscillation within them. This is something that you can't detect in fluorescence because in fluorescence it just looks flat. You can't see slight modulations. But you see in this movie now that this is the same thing as here. You can clearly see that things become dark and becomes bright, and that's because this thing is breathing, is kind of going up and down, and it's changing its contrast in front of our eyes. So we can analyze all of that and figure out a kind of a topography map and frequencies and all of that. So we are right now particularly excited to apply all of this to live cell imaging and especially virus infection. And here is a little example of the work that we're going to submit soon, hopefully. Here is a virus, and here's an actin tail. And again, we know this because we can label these to make sure. When we do these works, we always do fluorescence to make sure that we're not fooling ourselves or others. But then what the advantage of the label-free version is that you can look at this forever. So these are, again, this is another view. These are viruses. These are vaccinia viruses, slightly larger, particularly easy to see. And then you can see the actin tails that are kind of swirling around. It's known that these vaccinia viruses are driven at the end by the actin tail, for example, out of the cell. So we're studying these things. So that's kind of what I wanted to tell you about our iSCAT work. I want to take a few minutes still before I finish, but these were the results that I wanted to show. We're very excited for anyone who joins the game, and the iSCAT setup is remarkably simple. If you don't feel comfortable building it, then we will help you build it. But the analysis is a little more involved, so if you want to start from scratch, you might need a whole PhD to get into it and understand it. But we have an open source package that we're constantly kind of feeding, and we call that PySCAT because it's written in Python. And it's open source, so you can also modify it if you want to. With that, I'd like to thank all the people who, over the years, from year 2000, when Thomas Kalkbrenner saw the first iSCAT signal, all the way to today. These are a number of people, postdocs and PhD students, who have contributed to this journey. Marie Reischke is actually here. So she's the newest graduate student, and Shuan Zhang is the newest postdoc. All right, now I want to take a few minutes to put all of this in context. This is a version of something like IceCat that was actually done in the early 90s. What they were looking at were microtubules on a substrate. And this, remember, is in the early days of confocal microscopy. So confocal microscopes emerged in the 80s as commercial microscopes. And they looked at everything with a confocal microscope. And this group actually was smart enough to not just look at fluorescence, but also look at the incident light coming back. And they call that a confocal reflection interference microscope. So it's really the bigger brother of IceCat. But the point is that they're doing reflection. The instrument is exactly the same thing, but they're doing reflection in the sense that they're looking at larger objects, or they think they're looking at larger objects. If you remember the polarizability issue, then you can say that, okay, the signal that is coming from a microtubule in that experiment can be estimated as its volume within a diffraction-limited spot, which contributes to the signal. That would be something like the cross-section of the microtubule times its length within the size of a diffraction limit. So that amounts to about 80,000 cubic nanometer. Now, you have to compare that to the volume of a small protein, and that would be 64 cubic nanometer. So that's the journey that we've taken, going from 1990 to more around 2010 or 14, was to improve the signal-to-noise ratio by a factor of 1,000. But that's only because once you understood what exactly is behind this thing. And in that same spirit, when you're doing, if you really get to all the way to the noise limit, and then you need more signal, you can try to enhance it. And one way of enhancing it is to put it in a cavity. And many of you have been doing this, including our chairperson, for a very long time. Now, when you put something in a cavity, then the light goes and keeps going back and forth. Now, imagine with the same scattering cross-section kind of argument, what happens is that the photon goes through your atom or nanoparticle. There is a probability of sigma over A interaction. But then it comes back and goes back and forth by of the order of finesse divided by pi. So every time it gets an enhancement. So every time the probability that you actually see that there is something there is enhanced by this factor of finesse. But when you put it in a cavity, you have a larger mode area, typically in this kind of a Fabry-Perot cavity. And that, compared to a diffraction limited, makes you lose. So the figure of merit is the finesse divided by the mode area. And if you rewrite that, simply, it becomes quality factor divided by volume, which is the typical thing that any kind of a cavity person would have in mind. So, of course, when you do this work, if this is your enhancement factor, ideally you want to have as large of a Q and as little of a volume as possible. Sometimes it's not easy to get all of that at the same time, but this is kind of where you want to go. And of course, this is something that people in quantum optics have been doing on single atoms. We have shown this on a single molecule recently. And this is, again, by taking the molecule to 1.5 Kelvin so that its cross-section becomes large. And its dipole moment actually is not decoherent, so that it actually has a good interference. If you allow me, the claim of the bacteria undergoing a strong coupling was unfounded. It's not so easy to get to a strong coupling regime. So you need to have a very high degree of coherence. And this we can do at the single molecule level by going to a very low temperature. Now, when you put a nanoparticle in this cavity, of course, the first thing that comes to your mind is that the nanoparticle is going to scatter the light out. It's going to spoil the Q of the cavity. And it's true, if your nanoparticle is very large, it's going to do exactly that. But at some point when the nanoparticle is small enough, it's not going to do that. But you can show, again, that polarizability is the key factor. And you can derive, and this type of thing had been actually derived in the microwave domain, and we showed that again in an earlier work in a different context in the optical domain for microcavities. But what you see here is that the shift that you get of your resonance, again, is proportional to the polarizability and has to do with Q over V. So in that way, there's a clear parallel between your kind of atomic physics cavity QED and your sensing. And this type of thing, of course, has been done. Now, whether you have a microresonator or nano antenna, the physics is basically the same, because in both cases you have a resonance and you're trying to shift the resonance. And in both cases, it's the polarizability and the mode volume and Q that are important. And of course, you can then easily compare yourself and see what happens, which one is better. But my recommendation would be to always then compare that to no cavity or no antenna, because I think that quite often, in its purest form, you actually have a lot of signal. And of course, if you allow me to remind you again, I think Roman talked about this, this type of thing has a disadvantage that you need that mode area or mode volume, and that already automatically confines you, whereas if you're ideally you want to have as large of a sensor as possible that operates at the same time. Okay, with that, I would like to close, but I just flashed two works. One has been published, but it might be of interest to people who are actually interested in confining and controlling things. This is a tipless way of doing controlled nano antenna work. And this is something that's on the archive, should come out soon. And it's a way of creating a kind of an optical antenna for getting more photons if you're doing sensitive fluorescence in a solution. So we create a kind of a nanofluidic arrangement here that acts like an optical antenna that forces all the photons to go in this direction and not go up. And with that, I really come to an end. Thank you for your attention, and also advertise some postdoc positions if anyone is interested.
Thank you, Vahid, for this fantastic talk. So there's already a first question.
Thank you for a fantastic talk, very inspiring. And I assume that this is the last talk, so there's infinite time for questions.
I doubt that. I think I already have used
Okay, so I have two questions. So in the polarizability equation, the other factor, volume times index. So you have the index of the n is the index, right?
Yes, yes.
Yeah, so I guess the general question is, I didn't read this SS Nano paper, the one that Hirfield showed, but what is the possibility of taking ice cut into spectroscopy? I mean, what, instead of just...
Right, that's a good point. We have done a little bit of that in the context of plasmon resonances, because they have spectra and they have resonances. The only thing that makes your spectroscopy a little difficult is that it's a phase-sensitive signal. So position of the particle with respect to your reference changes the signal just as its spectral behavior does. And so there's a lot of potential to do that, but you have to be aware that it's not just a piece of cake.
Mm-hmm. So if it's not moving, it's possible.
That's right. I mean, even if it's moving, you can do it, but it's a little more complicated.
I see.
Yeah.
So the second just quick question is, coming from the quantum optics point of view, if you keep reducing the photon number and do this, I mean, would it be, what is the possibility of eyes cut, in sort of ghost imaging?
So we have done, there is a paper from, I think, 2009 or 10 or something, where we've done ISCAT on a nanoparticle with single photons. But that was a kind of fun experiment. You don't really win because we usually need we're short noise limited, so we actually want to always have a large number of photons to get a better signal to noise ratio. And to go to single photons you would have to have a good reason to do it. But we've done it. We've done it with a single molecule. We've done it with a single nanoparticle.
But sensitivity is not, does...
Again, the sensitivity is within your signal-to-noise ratio, so your signal-to-noise ratio at low photon level is, by definition, worse.
Right.
Vahid, fantastic work. Really enjoyed the presentation. So I have a question about the observation of the secreted proteins and exosomes. What sort of information will you get there? Because is it size? Is it the number? I mean, will you be looking at identity in some fashion?
Yeah, so what we're doing right now, I mean, there are different ways of doing that. There's some people who, for example, we're working together with a group that in microbiology that is interested in understanding how their parasites are secreting things. And so that's one way where you kind of know that something must be secreted and you want to quantify it. You want to know under what condition they secrete, you stimulate them, you drug them, whatever. So that's one application where you just document and then see what happens. But the other one is more exploratory, where you look and see what happens, even if you don't know what it is, but then you have to do more work. So right now we're combining our INTA with fluorescence. That's a kind of an obvious thing to want to do, so that you don't just get the size and the index of refraction, but you also get extra information about other things, antibodies or whatever that might attach or not. So there are lots of things that you could do. There isn't just one thing. It's just one more step in collecting data. That's the way I see it, yeah.
Lovely, thank you.
I have a question about precisely understanding the measurement data for a protein. When you get this histogram around the average size, is there scope that within that distribution there may actually be more information about something like conformation or unfolded protein, knowing precisely what is...
Yeah, so that's
measured.
one of our little bit of a mystery and weaknesses. We would love to have much narrower histograms. You would usually think, okay, well, yeah, I make a measurement and there's a certain width, but mass spectrometers' width is much smaller. So we're trying to understand where that width comes from. And I'm quite confident that we can make it narrower. Once you make it narrower, then you can look for heterogeneities in your sample, which must be there. But I think the first step was to see that you can recognize dimers from trimers from monomers. But now there is quite a bit of effort, not so much in our group, but by other groups to look for example, form factors and conformational changes and all that. You need to jack up your signal because you need better signal-to-noise ratio. But I think it's not impossible. And again, the way I see iSCAT is not just as an island, but it completely combines with everything else. It can combine with nanopores, it can combine with plasmonic traps. You can do all of these things at the same time. So that's, I think, how it's going to go forward. Yeah.
Thank you for the exciting talk. I wanted to ask, when you do iSCAT with fluorescence, do you have some sort of colocalization limitation there, or do you observe a phase shift in any way?
Phase shift because of?
When you do localization through iSCAT and you take a fluorescence image, is it like strictly colocalized together?
Yeah, usually it does. We've done some earlier work in around 2009 or so where you can see that. But you can screw things up in different ways, as usual, but it doesn't have to be that way, yeah.
You looked into the nucleus.
Yes. There is actually a figure about the nucleus in the paper. I didn't show it now. Now, about the nucleus, the thing is that the nucleus is very dense. We score particularly well when you have isolated features because our resolution is not better than the diffraction limit. Now, we see the nucleosomes, and what we particularly like is the topography of a nuclear envelope. So what we have is a little bit like doing AFM on the nuclear envelope in the live cell. So we're quite excited about connecting that to the type of a cell mechanics or signal transduction type of things that might be happening there by monitoring that. But we haven't invested that much time into that yet. But inside the nucleus, we're a little blind because there isn't much heterogeneity at the smaller scale.
Can I have
Yeah. We're very happy. I mean, we're somewhat limited in terms of workforce ourselves, but we're very, very happy to collaborate with anyone who wants to do this and just help them. I mean, maybe I should say we have already shipped one instrument as a kind of a at no cost type of a thing. We're happy to build devices for people if they don't want to build it themselves and help them get going.
So I have a question here.
Yeah.
Last question.
You show a linear relation between, for mass photometry, you show a linear relation between the mass and the scattering contrast, but actually the polarizability is scaling with the volume. So I don't know, how do you have, like for example, do you take two particles of the same volume, they will have a different scattering contrast?
I mentioned that briefly, that you might be surprised by that. That's how it turns out. And of course, that's how it turns out within the accuracy that we have right now. So if you were to go into it, at some point, the form factor must come in. So it's not even just the volume, but also the polarizability that I showed you. That was for a spherical particle. If you have something that is elongated, that form factor would also change a little bit. So there is a lot to be seen, but right now, the thing that everyone loves about this method is at the level of looking at monomers and dimers and all of that, which is a very easy thing to do because you just need to be able to resolve things by a factor of 2. But exactly where that central point is most probably not completely on the line.
Okay.
Okay. With that, I would like to thank Vahid one more time for his excellent talk.